Good morning. My name is Thomas Tucker, and this module will offer an introduction to configuring a Vpls on the Nokia 7750 service router platform. This module assumes the reader is familiar with the service router platform service architecture, as well as familiar with the concept of deploying Layer 2 services through LDP signal pseudo-wires. And as always, it's best to review the RFC prior to viewing this module. And in our particular case, it's going to be RFC 4762, which is VPLS using LDP signaling. All right, feel free to pause the video and review the service architecture for the Nokia SROS. And here's what our subscriber network is going to look like. We have a subscriber site R1 in Los Angeles, a subscriber site R2 in New York, and a subscriber site R3 in Dallas. And each of these subscriber sites are going to be on the same Ethernet segment. So the network address for all three is going to be 172.16.0.0. The subnet mask for all three is going to be a /24. And the broadcast address for all three is going to be 172.16.0.255. The only difference is our host addresses. So Los Angeles is going to be addressed .1, New York is going to be addressed .2, and Dallas is going to be addressed .3. And the end goal of our VPLS is to connect each subscriber site to the service provider, but from the subscriber's perspective, have the service provider's IP Mpls backbone emulate a virtual switch, or put each site within the same broadcast domain, or on the same Ethernet segment. So here's what it's going to look like from the subscriber's perspective. We're going to have a full mesh service distribution points or targeted LDP sessions, as well as a full mesh of pseudo wires. And what this is going to do is it's going to guarantee us a loop-free IP Mpls core. And the reason it's so important for this core to be loop-free is because, unlike a virtual private wire service, where it was a single point-to-point layer 2 circuit like an E-pipe, in the case of our virtual private LAN service, we do have the opportunity for broadcast storms and switching loops. And there are a million ways to deploy VPLS based on customer requirements. The way we're deploying it is just a vanilla full mesh VPLS. I mean, if you look at the RFC, this is pretty much the example that's given in the standard. Just 3 PE routers, 3 sites, and a full mesh of targeted LDP sessions and pseudo wires running between each. So the main attribute of VPLS, as we discussed earlier, is it turns the service provider into a virtual switch for the subscriber. And the way it does this is each provider edge router that the CPE is built off of or stubbed off of, it's going to learn the MAC addresses for the local customer premises equipment. And it's also going to learn the MAC addresses through the targeted LDP sessions for the remote customer premises equipment. So in the case of N1, our subscriber site in Los Angeles, R1, its MAC addresses all begin with alpha. So in N1's forwarding database for our VPLS instance, which we've given the service ID 65, it's learning those MAC addresses beginning with alpha through the service access point, or through the SAP, I should say. Likewise, when our other sites come online, so for example, our subscriber site in New York, its MAC addresses begin with Bravo, and our subscriber site in Dallas, its MAC addresses begin with Charlie. When these sites come online, router N1 will learn those CPE's MAC addresses through the appropriate targeted LDP session. So in the case of New York, whose MAC addresses begin with Bravo. It's going to learn those MACs through our pseudowire SDP 102:65, or I should say mesh SDP 102:65. And it's going to learn Dallas's MAC addresses, which all begin with Charlie, through the pseudowire mesh SDP 100:65, or through SDP 100. And this process is going to rinse and repeat on each provider edge router until they all have a valid MAC entry for each CPE that's participating in the subscriber's VPLS instance. And the number of MACs can vary. It can go from as many as 6 MAC addresses in an FDP, or FDB rather, to as few as 4. So I've seen that it really just sort of depends on how talkative that the switches are and how talkative that the CPEs are as well. So here's the life of a given VPLS customer payload. And if you reviewed our last module on VPWS, you'll notice that all I did was copy that particular slide and paste it here. That's because traffic will be label switched in the exact same fashion. The only difference being for our VPWS, or our ePipe, we had a service label of 87 because our service ID was 87. In the case of our VPLS, we're going to have a service label of 65 because our service ID is 65. But just briefly reviewing the life of this packet, this customer payload ingresses our ingress LER, label edge router, through the SAP 115:10. And this should actually be 20 because we're going to use the VLAN tag 20. Let me go ahead and correct this, because if I don't do it now, I may forget. Yeah, so this was literally just copied and pasted. All right, much better. So this customer payload is going to egress our customer site, and it's going to be encapsulated with a VLAN tag of 20. And it's going to ingress our provider edge router through the SAP 115:20. And based on this this ingress SAP, the provider edge router is going to be able to identify the service that this payload belongs to. So this customer payload will be multiplexed, and that will have a service label pushed on top of the payload. And based on the far end of our targeted LDP session, the customer payload will be further multiplexed with a transport label, letting each label switch router, or each router within the Mpls domain, allowing them to label switch this packet from our ingress label edge router to our egress label edge router, which in our case is N6. So customer payload comes into the SAP. The payload is multiplexed with a service label, then multiplexed with a transport label, creating our label stack, and its egress to the next hop, which in our case is N2. And when the datagram leaves our ingress label edge router and enters our label switch router, our label switch router is going to perform a swap operation on this transport label. So it's going to see the transport label of 101, and it's going to swap that 101 with the 202, and then egress that datagram to the next hop, which in our case is going to be R3. Just note that the service label will not be touched while this datagram is being label switched through the IP Mpls core. So once this datagram reaches our egress label edge router, which is N6, it's going to be demultiplexed. So the transport label is going to be popped off, exposing the service label. The service label is going to be examined and then popped off. And after this service label is demultiplexed, the router will recalculate the frame check sequence. It'll insert or it'll tag the frame with whatever VLAN is appropriate and forward it out the appropriate egress SAP onto the customer site. All right, so we are going to be adding an additional IP MPLS provider edge router. Its name is going to be N7, and it's going to host our subscriber site in Dallas, R3. And N7 is going to be stubbed off of router N3. And on router N3, we're going to have the physical port 113. We're going to bind that physical port to the logical router interface 2N7. And we're going to assign that logical router interface the IP address or the logical IP address of 10.3.7.3/28. And on router N7, we're going to have the physical port 111 bound to the logical router interface 2N3. And we're going to assign the logical IP address 10.3.7.7/28 to that logical router interface. And since we're deploying router N7 sort of out of the box, we're also going to assign the logical IP address 7.7.7.7/32 to N7's system interface as well. So here's what our deployment is going to look like. First, we're going to go through the system configuration, which is we're going to assign our system a name. In our case, it's going to be N7. Then we're going to take care of the hardware configuration. So we're going to configure our input-output module along with our media-dependent adapter. Then we're going to configure our physical network port. And this is what's going to connect N7 to N3. So all we're doing here is we're assigning it as high of an MTU as SROS will allow, which in our case is 9212. Then our physical access port configuration. We're going to take physical port 115, we're going to turn it into an access port and configure it to accept .1Q VLAN tags. So we would expect the MTU to be 1518 for our physical access port. 1514 plus the 4 bytes for our VLAN tag. Then we're going to get into our logical router interface and router ID configuration. So just like on our diagram, we're going to assign our system interface the address all 7s/32. And we're going to assign our interface connecting to N3 the address 10.3.7.7/28, as well as bind it to the physical port 111 and configure BFD on it as well. And lastly, we're going to configure our router ID of 7.7.7.7. And these BFD timers normally, or I think, when did we configure BFD? I think maybe it was module 2 or 3. We were using 100, 100 with a multiplier of 3. Since we're starting to build the network with so many routers and we're deploying services, I'm not sure if the hardware that these virtual routers are running on can keep up with BFD that aggressively. Or I should say, keep up with a BFD deployment that's as aggressive as 100, 103. So if we notice BFDs tearing down our adjacencies, we're going to relax the BFD attributes network-wide to 500, 500 with a multiplier of 20. So getting into our interior gateway protocol, in our case, intermediate system to intermediate system, we're going to configure our intermediate system as a level 2 IS. We're going to assign it to the area 49.00. We're going to make sure it's using wide metrics only. We're going to add our logical router interface system to our ISIS domain as a level 2 interface. And we're also going to make it passive because while we want this address to be redistributed into our IGP, we don't want any adjacencies to form over that address. And we're going to add the logical router interface 2 and 3. We're going to make it a level 2 circuit as well as point-to-point. We're going to enable a BFD across it and assign it the metric of 5,000. And for our MPLS service, we're going to add the network interface and system interface to MPLS. And for LDP, we're going to add the network interface. And we're also going to make these, we're going to make the protocol LDP operational and the service MPLS operational as well with the no shutdown commands. And here's our VPLS configuration. Again, SROS makes deploying services very simple. Everything's very straightforward. So first, we configure the customer, then we configure our targeted LDP sessions, then we configure our service. So with the customer, we're going to be using customer 20. With the targeted LDP sessions or service distribution points, since this is a VPLS, we're going to have a full mesh. So SDP 100 is going to go to router N7, and SDP 102 is going to go to router N6. And just going back to sort of the working to how the service distribution points work, we are going to specify MPLS as the delivery method because by default, SROS uses GRE. And we are going to enable LDP signaled label switch to paths for this targeted LDP session as well. So that's where the MPLS attribute within the configure service SDP statement comes from. And that's where the LDP attribute within that context comes from. And our last step is to configure the service. And once we configure the service, we bind our SAP to that service. And once we bind our SAP to that service, we bring up our pseudo wires, which in our case is going to be mesh SDP 100 and mesh SDP 102. So let's take a look at our goals and see, while we review our goals, let's just build our service provider network and get these devices up and running. So like we said, we're going to have router N7 stubbed off of N3. We're going to have a switch that's going to perform our trunking, and our CPE, which is going to represent our subscriber site in Dallas. Let's go ahead and connect those. So router N7's physical port 111 is going to go to router N3's physical port 113. Router N7's physical port 115, which is our SAP, is going to connect to our switch over FA115. Again, this is just going to be a run-of-the-mill trunk port. And our switches FA10 is going to connect to our CPE's gig 00. Again, it's going to be a run-of-the-mill trunk port as well. Let's go ahead and get these devices started. Looks like N2 wasn't happy, so we'll restart N2. All right, much better. All right, so let's make sure our service routers are still booting up here. a little skeptical of N7. It's taking quite a bit of time. Let's reboot N7 just to make sure he didn't hang. So N2's up. So at this point, we're just waiting on N7. So let's go back to our goals. Let's see. So we're going to, and by the way, somewhere along the line, I stopped putting the goals at the beginning of the presentations and started putting them at the end. Not sure why I did it, but it is what it is. But anyway, we're going to create a subscriber network connecting to the service provider. So on R1, which is going to be our site in Los Angeles, we're going to use the sub interface .20 and give it the address .1. For router R2, representing our subscriber site in New York, same sub interface, we're going to give it the address .2. For our subscriber site R3, representing Dallas, we're going to use the same sub interface, but we're going to address it .3. And again, all these sub interfaces are going to use the VLAN tag of 20. Then on our, so I wonder if we should do this one at the time. Yeah, okay, so we'll go ahead and get our subscriber network out the way. One second here. Sunlight is just killing me. Okay, there we go. All right, so for router R1, our sub interface is going to be gig00.20, and it's going to be 172.16.0.1/24. Router R2, we're going to do the same. Encapsulation .1Q 20, and our IP address 172.16.0.2. Placing it on that same /24 network. And on router R3, our physical port is going to be gig00. Our sub interface is going to be .20. Encapsulation is going to be .1Q VLAN tag 20. And our address for Dallas is going to be .3. And of course, it's going to be placed on that same subnet. All right, so we've taken care of the CPEs. Now for the switches, we do have an E-pipe using VLAN 10 running through switch 1 and switch 2, but our VPLS is going to use VLAN 20, but I'll enable VLAN 10 just for the sake of not having anything down. But again, our VPLS is going to use VLAN 20. So on switch 1, I'm just going to go into VLAN 10, state active, and repeat this with VLAN 20. Switch 2, we're going to do the same. VLAN 10, state active. And repeat this with VLAN 20. And in the case of switch 3, since all we're going to be using switch 3 for at this point is our VPLS, we're just going to enable VLAN 20 within it. Of course. And then I go and enable VLAN 10. All right, and also with switch 3, we're going to have to configure our trunk ports. FA10 is going to be the trunk connecting to our CPE, and FA115 is going to be the trunk connecting to our PE. Let's go ahead and get that taken care of. FA10, switch port mode trunk. FA115, switch port mode trunk as well. Let's take a look at spanning tree. And spanning tree just being spanning tree, man. Taking its sweet time. But yeah, so VLAN 20 is being forwarded. That's what we want. VLAN 20, I'm sorry, it's being forwarded. Same on switch 2, VLAN 20 is being forwarded. And on switch 1 as well, VLAN 20 is being forwarded. So we are good to go there. All right, so we've got our subscriber network taken care of at this point. Now we're going to move on to our customer. In our case, we're going to use a customer ID of 20 to host the subscriber services. Admin, of course, is the default username and password. So we're going to go into the configure service context, and we're going to configure our customer, which is going to be 20. We're going to give them the description, subscriber B incorporated, contact admin at subb.com, I guess. Contact, because it's Little Rock, 501-999-9999. So here's our configuration for the customer ID of 20. And we can go ahead and do that on our other, well, we're not going to do that on our other edges at the moment. Let's just get through this VPLS first. All right. And once we have the customer created, let's go back to this one. This is from the perspective of N1, by the way. So we've got our customer created with the ID of 20. Next, we're going to configure our targeted LDP sessions or our service tunnels. So our service tunnel being represented by SDP 100. Our service tunnel being represented by SDP 100 is going to connect to router N7, and our service tunnel being represented by SDP 102 is going to connect to router N6. And again, we're going to specify Mpls as the delivery method and enable LDP signaled label switched paths. All right. So exit gets us back into the service context. Once we're within the service context, we can go ahead and create our SDP 100. Specify Mpls as the delivery method. Description, this is going to go to N7. And our far end is going to be N7's system address. And we are going to enable LDP signaled LSPs. here's our configuration for SDP 100. Next, SDP 102 is going to go to router N6. So SDP 102, specify Mpls as the delivery method. Our description is to N6. The far end is going to be router N6's system address. And we're going to enable LDP signaled label switch to paths. Here's the configuration for our service tunnel to N6. All right, so once we've got our service tunnels configured, we can go ahead and configure our VPLS service. So in our example, we were going to use the VPLS service ID of 65 for the customer 20, for the customer ID of 20 rather. And our description, I believe it was VPLS instance for subscriber be incorporated. And we're going to also configure this for our service name, because this is a field that makes your job as a network operator a lot easier, but teams that deploy services, like the service delivery team, rarely use, which is the service name attribute. And what this does is when we enter the command show service using, it allows us to very quickly identify our particular service. See, so our ePipe didn't have a service name, although it probably has a description. Let's go back for a second and look at our ePipe. Yeah, so it has a description, yet no service name. So as a network operator, if you wanted to quickly identify the services that were running on this router and didn't want to dig through the description, you would have to rely on this service name field being populated. So we're going to go ahead and populate this for our ePipe as well. So service using. Okay, so much better. So getting back to VPLS 65. Let's see. Let's configure this earlier. Let's get rid of these. Okay, much better. So here's our configuration for our VPLS instance so far. Once we have the description and the service name taken care of, we can now bind the SAP to our service. In our case, it's going to be the physical port 115 with the service delimiting VLAN tag of 20. SAP 115:20 create, no shutdown. And once we have our SAP bound to our service, we can go ahead and build our pseudo wires, which in our case is going to be, let's see, all right, so in our case, it's going to be SDP or Mesh SDP 100 and Mesh SDP 102. So mesh SDP 100, create no shutdown. Mesh SDP 102, create no shutdown. And what this does is this builds our pseudo wires on router N1 that's going to come up through our service tunnel, SDP 100 and 102, to our far end PE routers, which in the case of SDP 100 is going to be router N7, and in the case of SDP 102 is going to be router N6. So here's our VPLS configuration. Again, from router N1's perspective. So let's go ahead and rinse and repeat this on routers N6 and N7. So we're going to go ahead and configure the customer. Configure service. Well, let's go into the configure service context. Customer 20 create. Then let's build our service distribution points. And in the case of router N6, we're going to have SDP 102 going to router N1 and SDP 101 going to router N7. So on router N6, we're going to specify SDP 102, the delivery type Mpls. Our description is going to be to N1. Our far end is going to be router N1 system address. And we're going to enable LVP signaled LSPs as well. So here's the configuration for our service distribution point on router N6 connecting to router N1. And let's see, SDP 101, specify Mpls as the delivery method. Our description, this is going to go to N7. Our far end is going to be router N7's system address. And again, we're going to enable LVP signaled LSPs and bring it operational. So this is the configuration for our targeted LVP session between N6 and N7. So once we've got our targeted LVP sessions built, just like on router N1, we can go ahead and create our service. It's going to be VPLS with a service ID of 65 for a customer with an ID of 20. And we're going to go ahead and bind their SAP, which is going to be physical port 115, the service delimiting VLAN tag of 20, create no shutdown. And we're going to go ahead and build our pseudo wires as well. And in our case, it's going to be mesh SDP 102 and mesh SDP 101. So here is the VPLS configuration for router N6. Again, we have our SAP 115:20. We have our targeted LVP session 101 going to router N7, and our target LVP session 102 going to router N1. So let's circle back to router N7, which was going to be our brand new PE router. And you can see it's blank config. So default username and password is admin. And we're going to cheat a little bit. The commands that we went over in the presentation, these are the exact same commands. I'm just going to use the genduso method and paste these in here and deploy the service box. And again, like in our earlier videos, the reason why the prepending these commands with a / is so useful is because it allows you to enter the command within any context. So if you were in the configure system or configure service context, by prepending this command with a /, you would be able to configure the logical router interface 2 and 3 you'd be able to bind that physical port to that logical router interface without having to back out of the service configuration context, go into the router context, then go into the interface context within the router context. So it makes copying and pasting commands extremely easy. So now that this is done, let's go ahead and check our adjacencies. And it looks like we are stuck in an init state because that hold down timer, 30 seconds, is coming down. All right, so yeah, so that hold down timer, it's 30 seconds if I'm not mistaken, but it went all the way to 0 and reset, and we're still stuck in our init state. So let's check the logs and see exactly what's going on here. All right, so what is our logs telling us? By the way, I did the command. Let me, all right, so I did the command show log ID 99, application ISIS. These logs in SROS are very verbose, which is a good thing. But you can specify or you can key in on different applications. So, for example, you have all these options: application assurance, BFD, anything dealing with the chassis, DHCP, link layer discovery protocol, NAT, Christ, if you're running NAT on SROS, that's very, you must have an interesting network, or you must be rich. LDP, debug, OSPF, etc. So we want to key in on the ISIS protocol. So we're going to specify application ISIS to try to figure out what's going on here. So what is the router telling us? Well, it's telling us that it rejected the adjacency. Let's see. So adjacency status changed to initializing, changed to down. All right, so it looks like it's just rejecting the adjacency. So instead of keying in on the application ISIS, I'm going to take a look at all the logs and see if something else is causing this adjacency to bounce. And it looks like BFD's in here. Yeah, so since we overlaid intermediate system to intermediate system with bidirectional forwarding detection, BFD is what controls these adjacencies. So if BFD isn't happy, then that adjacency isn't going to be happy either. So it looks like the session cleared and session deleted. So it looks like BFD is bouncing. So let's take a look at our BFD sessions. And it is down. Interesting is it transferred 26 BFD packets but received none. So it isn't getting anything from router N3. And the reason it isn't getting anything from router N3, figure router N3. Let's see, we'll rip out anything we don't need. And this is going to be 113. We don't need to build a SAP. This is going to be 7.3. All this is going to be 2N7. 113. Aren't going to need a router ID. N7, N7. Oops. Router 2 and 3, interface 2 and 3 does not exist, and it isn't supposed to. All right, so let's go ahead and save our config on router N3 and save our config on router N7 as well. And let's see if our adjacency is happy now. Init with that hold down timer expiring, and it still isn't happy. So let's take a look at our log file again. Let's see, 12:07:39. I'm just going to set the timestamp. Well, yeah, so that's pretty recent. Let's see if BFD's up. BFD's still down. Transferred 11 and received 0. What's going on router N3? So BFD isn't even configured on the interface to N7. It is. Let's go ahead and relax everything. Receive 500, multiplier 20. So router BFD session. Is it in ISIS? It is in ISIS. That is pretty strange. It's not receiving any BFD packets across this link. Let's see if we get any new error messages. So it looks like BFD is still bouncing. So let's just go ahead and relax all of our BFD timers. All right, so that takes care of N7. All right, so on router N1, we're going to relax the BFD timers on our logical router interface to N2. On N2, we're going to relax the BFD timers on our logical router interface to N1 as well as to N3. The same thing on router N3. Router N5 just is not happy. Let's go ahead and reboot him. Much better. Let's go ahead and take care of router N6. And router N7, we've taken care of that already. And our config should be saved on everything. Okay, good. Now let's check out BFD. Still down. And our net adjacency is still stuck in a net. Guess we should we do some debugging? Why not? Why not? We'll do some debugging. Configure log ID, we'll call it 66. From debug trace to session. And shut down. Let's debug router ISIS. Adjacency. Let's see what this gives us. It's telling us it's not bringing up the level 2 adjacency due to BFD being down. Let's take a look at these. Packets. Okay, I see what the problem is. We are receiving an ISIS protocol data unit that contains an authentication TLV. However, in router N7's ISIS context, we don't have authentication configured. So we're receiving a PDU from router N3 that contains this authentication TLV, MD5 with our password, but we're sending a PDU with no authentication. So it's not going to work. So let's go ahead and copy this, which is our authentication key. I can't remember what it was. It's like my ISIS key or something. And our authentication type, which is MD5. Let's go ahead and paste that. Let's see what happens. And like magic, our adjacency is up. Let's take a look at BFD. And we are now transferring and receiving BFD packets. So the problem with that adjacency not coming up again was the fact that we were receiving an ISIS protocol data unit that contained an authentication TLV or type length value. However, in the ISIS protocol data unit that we were transferring, we had no authentication TLV. So ISIS worked as it should have. So now if we just do that same debug command, we should be sending and receiving those authentication TLVs. All right, so here's our PDU that's received. It has its authentication TLV. And here's our PDU that was transferred. And as we can see now, contains that authentication TLV. So we're good to go there. Let's check our adjacency one more time, and it's up. So now let's check our routes. We should have ISIS routes to all the systems in our routing domain. So router N1, N2, N3, N4, N5, and N6. And we can ping both of our edges just to make sure that traffic can get from one edge to the other. Perfect. So that PE router is deployed at this point. So I guess we can go ahead and build the service on router N7. We have it built on router N6 already. So again, we're going to enter the configure service context, configure our customer with an ID of 20. After that, we're going to configure our service distribution points. And in the case of router N7, SDP 100 is going to go to router N1, and SDP 101 is going to go to router N6. So SDP 100 specify Mpls as the delivery type. So the far end for 100 is going to be router N1. We're going to enable LDP signaled LSPs. And here's the configuration on router N7 for our targeted LDP session to router N1. Now we're going to build SDP 101, specify Mpls as the delivery method. The far end for SDP 101 is going to be router N6. So N6 is system address. And we're going to enable LDP signaled LSPs. And here's our targeted LDP session to router N6. So once we have both of our targeted LDP sessions built, we can go ahead and build our service, which is going to be Vpls with a service ID of 65 for the customer with an ID of 20. And we're going to define the SAP, which is going to be our physical port 115, along with a service delimiting VLAN tag of 20. And we're going to build our pseudo wires. Again, it's going to be mesh SDP 100, which is our targeted LDP session to N1, or pseudo wire, I should say, and mesh SDP 101, which is our pseudo wire to router N6. So here's our Vpls configuration on router N7. Go ahead and save that. All right, so let's jump back to our goals here. All right, so we've created the customer with an ID of 20 on all of our PEs. We've created our targeted LDP sessions or service distribution points on all of our PEs in a full mesh. We've created our VPLS instance on all of our PEs for the subscriber. We've bound our SAP to each VPLS service. And we've created our full mesh of pseudowires or mesh SDP pseudowires through our service distribution point within our VPLS instance. So now let's verify the service's label redistribution. So we'll go to N1 and we'll check out our label information base for our VPLS instance using the command show router. Almost forgot. Show router LDP binding services, service ID 65, FEC 128. So we can see that router N1 generated a ingress VC label of 65 to represent the service. And by the way, this is purely by chance that these labels, one, were generated ending in the same digits as our service ID. And it's also pure chance that each router N1 generated 65 to represent this VPLS instance, and our far end router N6 also generated the label of 65 to represent this VPLS instance. Again, that's just pure chance. But we can see that, so to represent the VPLS instance for the pseudowire connecting to router N6, router N1 generated the label of 65. And to represent the pseudowire going to router N7, router N1 generated the label of 62. So if we go into router N6, we should see that N6 has generated a label for the same pseudowire, an ingress VC label of 65. And we should see that router N7 has generated an ingress VC label of 64 for the pseudowire. So let's go into router N6. Show router LDP bindings, services, service ID 65, FEC 128. And again, as we saw in router N1, router N6 has generated the ingress VC label of 65 for the pseudowire. And router N6 has also generated the virtual circuit ID, the ingress virtual circuit ID label, or ingress virtual circuit label of 62 for the pseudowire, while router N7 generated the egress VC label of 63 for the pseudowire. So jumping into router N7, show router LDP bindings, services, service ID 65 FEC 128. Router N7 generated the label 64 to represent the pseudowire. Router N1 signaled the label of 62 to represent the pseudowire. Router N7 generated the label of 63 to represent the pseudowire. And router N6 generated the label of 62, generated and signaled the label of 62 to represent the pseudowire. So we can see our label redistribution is working as we'd like it to. So next, we will verify the service's operational status through the following OAM commands: SDP ping, SDP MTU, service ping, virtual circuit, I think that's connection verification ping, and virtual circuit, it's either connection or connectivity verification trace. Might leave out the SDP MTU because that's more or less just an MTU sweep. With X being the minimum, Y being the maximum, Z being the value you want to step up by. So if X was 1500 and Y was 2000 and Z was, I don't know, 100, um, we would see 5 iterations of that SDP MTU command. It would test the MTU at 1500 bytes, test it at 1600 bytes, test it at 1700 bytes, 1800, 1900, and when it hits 2000, that's going to be its limit. So it'll either go to the limit you specify, or it'll find that limit based on whatever that maximum is. So if we had a limit of 9,000, well, if our MTU across a given circuit was 9,000, we'll say 4,000, and we specified a minimum of 3,000 and a maximum of 9,000, and we wanted it to step by, I don't know, 1,500 bytes, then once this command gets to, let's see, so if we started at 1,500 and we were stepping by 1,500 bytes, and the maximum was 4,000, well, the link was configured for 9,000, and maybe our maximum path MTU was 4,000, then we would step from 1,500 to 3,000, and SROS would attempt to step from 3,000 to 4,500, but when it realizes it can't ping across the link at that value, it'll sort of reduce it. And I can't remember what it reduces the sweep by, but it'll reduce the sweep until it can successfully pass traffic across that link with an MTU greater than 3,500, but less than 4,000. So it'll find that maximum MTU for you. So that's a long way to say we're going to skip that MTU sweep command, but we will see what the others do, and we'll actually incorporate Wireshark to see what kind of traffic we're seeing with these commands. All right, so let's just filter on Mpls. All right, so the first one was an SDP ping. So let's do this from router N1. OEM SDP ping 100. And sent and reply received. So let's see what Wireshark captured. All right. So it looks like, oh, this is kind of interesting. So what we received is on the left, and what we sent is on the right. So we sent a Mpls datagram, yet we received a GRE tunneled packet. And I guess that's just a behavior of the software itself, maybe. But if we sent a datagram, I would expect us to receive a datagram as well. So SDP ping sends a datagram, but replies with a GRE tunnel packet. That was for 100, which is our session to N7. Now 102 is our session to N6. And that result was sent and received as well. Let's try the OAM service ping. IP address. Let's do router N6. Service ID 65. Local and remote SDP. Looks like this reply was received as well. Let's see what Wireshark has for us. Let's do that one more time. There we go. All right, so let's see what happened this time. This is what we sent. This is what we received. So this is what I would expect. We sent a MPLS label stack, and we received an MPLS label stack as well. And looks like we can actually identify our tags. Our outer or transport label is 66, and our inner or service label is 65. And that's with traffic originating from N1 destined for N6. And with traffic originating from N6 destined for N1, our transport label was 71. And of course, our service label was still 65. So just for proof of concept, we can jump into router N6 and look at the label that's in use for the forwarding equivalence class 1.1.1.1, which is router N1 system address, and verify that it is indeed 13.10.71. So let's go into router N6. We're going to take a look at the active label. So we're going to be looking in our LFIB, our label forwarding information base at this point, using the command show router, LDP bindings, active, prefix is prefix. Let's do router N1 system address. So we have a 69, which doesn't make sense. I would expect a 71. Let's see, look at this label stack again. That's odd. So let's go to router N1 and see if our active label for router N6's system address is 66. Show router LDP bindings, active prefix is prefix, and router N6's system address. So that makes sense. Router N1 is pushing the label of 66 onto traffic destined for N6. However, I would expect router N6 to push the label of 71 onto traffic destined for N1. Instead here, it says it's pushing the label of 69. Let's see, show router LDP bindings active. So 71 is for router N5's system address. Let's go into router N5 and see what label it has for router N1 system address. So router LDP bindings, active prefix is prefix. Switch swapping. All right, so we're going to step through MPLS one hop at the time to see exactly where this 71 is coming from. All right, so for traffic originating on N6 destined for N1, a label of 69 gets pushed onto it, and it's egressed to router N5. So when that traffic with a label of 69 ingresses router N5. Router N5 swaps that label of 69 with the label of 68 and forwards it to router N4. And when router N4 receives traffic labeled 68, it swaps the 68 for 68 and forwards it to router N3. And again, when router N3 receives traffic with a label of 68, it swaps that 68 for 68 and forwards it to router N2. Okay, so here's where our 71's coming from. Looking at the wrong router because I'm a genius. So when traffic ingresses router N2 with a label of 68, router N2 swaps that label of 68 for 71 and forwards that traffic to N1. And of course, when N1 receives that traffic with the label of 71, it pops it. So this packet that we're seeing, this label switched packet, is actually coming from router N2, destined for router N1. That's why our outermost label appears as 71. But what I have to do now is close PowerShell, but I'm going to snip this wire between router N6 and N5 just to capture that. I'm going to rerun the same service ping command on router N1, but I want to capture the traffic, that datagram between router N6 and N5, just so that we can see that outermost label is going to be 69. So let's take care of that. All right, so again, this is N5 to N6. We're going to rerun this service ping command and see what our outermost label is. Okay, so here we go. Here's our 69. All right, so here's our traffic from N7 destined to, from N6, I'm sorry, destined to N1 with our outer label of 69. And here's another packet, most probably from N5 with the outer label of 71. All right. So this packet that we see on the left with our outer label of 71 and our inner label of 65, this is a label switch packet that came from router N5 destined for router N6. And on the right, we have our Mpls datagram with an outermost label of 69. This is a label switch packet that originated from N6 that's destined for N1. So just like we stepped through each router and took a look at our LFIB, if we were to perform packet captures on each of these links, we would see these same label values. Oops. Didn't quite mean to delete the entire link. All right, so we've still got our packet capture between N1 and N2 going. And Router N3 just rebooted itself, as well as N4. Must be taking a while. Let's see how much time we have on this guy. 5 minutes. Might as well just reboot this now. All right, so we have examined the packet captures for the OAM SDP ping command. We saw that it sent a MPLS datagram, yet the far end replied with the GRE tunneled IP packet. We skipped the MTU sweep. We performed and did a packet capture on the service ping command. And we saw that with the service ping command, it looks like what it does is it actually emulates a label stacked datagram for our VPLS instance and tests the service from end to end being from PE router to PE router. So it'll generate a datagram. It will multiplex it with our service label, which is 65, and then further multiplex it or label stack it with the transport label, which in our case was 66, and send that test payload to the far end PE. And if everything is successful, that far end PE will reply with a inner or service label of 65, as well as a stacked label or transport label of whatever value corresponds to the forwarding equivalence class for our far end PE router system address. Some pretty interesting stuff. So now when these routers come back, we're going to take care of the vccv ping and vccv trace commands as well. Looks like they should all be back. All right, good deal. So let's see, VCC ping. And looks like there's a lot to this. We're going to use our pseudowire 100, which is between N1 and N7. So one packet was sent, one packet was received. So this confirms that our pseudowire is functioning between N1 and N7. Now let's try our pseudowire between N1 and N6. One packet sent, one packet received. So we see that's functioning as well. Now let's send a few and go to Wireshark and see what Wireshark has. All right, so it looks like this. There's this invisible drop-down menu that keeps getting in the way. So on the left, we have what we sent, and on the right, we have our reply. So it looks like for the VCCV ping test, 5 from 7.7.7.7 via control channel. So we know that this is testing our pseudo wire, but I'm looking at this label stack, and it's strange that we have our pseudo wire label at the top, and another label of 64 as our innermost label. Our source is our system address, but we're destined for localhost. And if that's the case, how exactly does N7 know to reply to N1? Target FEC stack. Let's see what's in here. Pseudo wire. Okay, so it's within our MPLS echo. You know, there's got to be a standard for this. As a matter of fact, I know that there's a standard for this. It's 50 something. 5085 maybe? Yep, 5085. All right, so pseudowire virtual circuit connectivity verification, a control channel for pseudowires. So this is all part of RFC 5085, updated by RFC 5586. I would encourage you to read this thoroughly. Looks like I've looked at this in the past, but I still don't have a thorough understanding of exactly how it works. So I've got the what, just not the how. So if anyone's interested, RFC 5085 is for our VCCV, and it's been updated by RFC 5586. Interesting. Let's go back to our last goal, or our last verification, I should say. Our last OAM verification is going to be VCCV trace. And here's our pseudo wire connecting to router N7. And it's one hop away, which we would expect. And then here's our pseudo wire connected to router N6. And it's one hop away as we would expect. Why is it one hop away? Let's go back to our diagram. And you can review the video on link LDP and targeted LDP as well. But targeted LDP in and of itself allows the redistribution of labels between non-directly connected peers. So in an example like this, the flavor of LDP we have running between N1 and N2 and N2 and N3 and N3 and N4, etc., is link LDP. So since these neighbors are directly connected, link LDP is what's allowing the redistribution and the signaling of label information amongst those peers. But in the case of our router edge routers, we almost want to trick the routers into thinking they're directly connected. So we know that physically it takes several hops to get from router N1 to N6. And you know what? OEM LSP trace might even be a better one. And it is. So we see that from an Mpls perspective, we are several hops away from router N6. We go through router N2, N3, N4, and N5. I should say from a link LDP perspective. But from a targeted LDP perspective, router N1 and N6 are, and I say this in air quotes, directly connected. So from targeted LDP's perspective, router N6 really is a single hop away from router N1. So if we run a LSP trace, which traces out the link LDP signal path, you can see that we have several MPLS LSRs in our LSP. But if we run a VCCV trace, which is tracing out the hops in our targeted LDP session, we can see that we have a single hop. So it's directly from router N1 to N6. Let's look at this in Wireshark. Let's close these. And just to make sure, run a new one. So this is our request, and this is our reply. And let's see what has changed here. So they look pretty. It looks pretty similar to the vccv ping command. It looks like the underlying mechanisms are exactly the same, except one attempts to trace out the targeted LDP session path. But as we can see, these packets look very similar. It might be worth actually doing a video on maybe troubleshooting Vpls, because it seems like VCCV is pretty deep. For it to only be 26 pages. Yeah, so I'm going to have to dig into this quite a bit more and gain a full understanding. And if it's worth doing a video on, I'll do a video on it. But these types of commands, it seems, are sort of reserved for very complex topologies. Like if we had a target LDP session several hops away, which would be not insane, but when and why would you ever do that? But as you can see, there are a ton of different attributes we can use when it comes to this OAC virtual circuit connectivity verification. Did I get it right? Yep, cool. So when it comes to this virtual circuit connectivity verification, looks like there's a ton of attributes that we could use, or a ton of knobs that we could play around with in order to troubleshoot our pseudo wire. So that takes care of OAM, and we verified that everything was functioning properly, from our targeted LDP session to our VPLS service to our pseudo wires. So next, we're going to verify the MAC address entry in each provider edge's forwarding database. And to do that, we use the command show service ID 65, since that's our VPLS service ID, FDB, or forwarding database, detail. So in router N1's forwarding database, we have the MAC address for our switch, SW1, and we're learning that through our SAP 115:20. And we also have the MAC address for our switch number 3 that we're learning through SDP 100. Let's go back to our diagram. So we're learning the MAC address, and again, just there are switches between the CPEs and provider edges, but we're learning the MAC address for our switch between R1 and N1 through our SAP 115:20. We're also learning the MAC address for our switch between R3 and N7 through SDP 100, or specifically through our pseudo wire, SDP 100:65. So let's do this on our other edges. Router N6, show service, ID 65, FDB detail. And on router 6, we see that we have the MAC address for switch 1 that we're learning through SDP 102. And we have the MAC address for switch 3 that we're learning through SDP 101. So now let's repeat this on router N7. Show service ID 65 FDB detail. And on router N7, we can see that we're learning the MAC address for switch 1 through our pseudowire SDP 100:65. And we're learning the MAC address for switch 3 directly through our SAP physical port 115 with the service delimiting view lane tag 20. So now let's ping each site in the subscriber's VPLS to verify reachability and examine each CPE's ARP table. Let's see, we can do this a few ways. We could ping them individually, or we could ping the network address and the broadcast address for our sites. And these became unresponsive, so I'm just going to close those sessions out and open them back up. All right, so on router N1, we're going to ping the network address, router R1, I'm sorry, which is our site in Los Angeles. We're going to ping the network address for our Ethernet segment. Let's go back to our diagram here. So again, on router R1, which is our site in Los Angeles, we're going to ping this network address. And if these other sites, R2 in New York and R3 in Dallas, if they truly are on this Ethernet segment along with R1, or if they're all part of this broadcast domain, then they should reply to this ping targeting the network address. Likewise, on R2, which is our site in New York, we're going to ping the broadcast address, which is 172.16.0.255. And just like in the case of R1, if these other sites, Los Angeles and Dallas, are on the same Ethernet segment, then they should reply to ICMP echo requests targeting this network's broadcast address, which again is 172.16.0.255. And on R3, we'll just do it the old-fashioned way. We'll ping the hosts individually. So that's our network address. That's our broadcast address. And you're going to get them all individually. So far connectivity between Dallas and Los Angeles is broken. Let's try Dallas to New York. And the connectivity between Dallas and New York is broken as well. So let's see what's going on. All right, so from our replies, we see that when we ping the network address from router R1, which is Los Angeles, router R2, which is New York, did reply. And when we ping the broadcast address from router R2, which is New York, router R1, which is Los Angeles, did reply. So these sites, New York and Los Angeles, are functioning just fine. However, our site in Dallas seems to be completely isolated. So let's start troubleshooting. First, let's begin with the physical port on router R3. Our physical port is OpperUp. We have input and output, so we know our port is functioning. Let's take a look at the config. Config looks good. Let's take a look at our sub interface. Configuring our sub interface looks good. And let's just look at the properties. All right, so working our way from the customer premises through the demarcation point, let's check out our switch. And let's just verify that our VLAN, looks like the switch has become inactive. So all right, so let's just verify that VLAN 20 is still being forwarded. And it is being forwarded out FA10, which is our connection to the CPE, as well as FA115, which is our connection to the PE router. So now let's step into our PE. And we know that VPLS within the service provider's IP MPLS domain at this point is working. So the only thing that isn't working is the VPLS from the provider edge N7 to the customer premises equipment R3. So if we look at the forwarding database on N7, we can see that we do have entries for the MAC address. Let's see, 101 would be N6. Okay, so we have the MAC address for N6, as well as the MAC address for, the MAC address for R2, as well as the MAC address for R1. And we also have the MAC address for switch 1 that we're learning through the pseudowire SDP100. Now, interestingly enough, we're learning the MAC address for our switch 3, directly through our SAP, which leads me to believe the problem is further downstream at the customer edge. So let's just look at our VPLS. So service ID 65. All match ignore case flag. Yeah, no flags on the VPLS. So now we're going to focus on our switch. Let's see. And it seems like FA115 is functioning just fine because, again, we're learning this MAC address, Charlie 205, ending Foxtrot 10 Foxtrot. Charlie 205, ending Foxtrot 10 Foxtrot. However, we aren't learning the MAC address for our CPE, which is just Charlie Alpha 06. So let's take a look at our switch. Looks good. Circle back around to R3. VLAN 20. VLAN 20. This is very odd. Let's try a rip and rebuild. And from what I can tell, it should be working. So we at least know that VPLS is working up until this guy, or I should say it's working network wide up until this guy. For some reason, our CPE R3's MAC address isn't making it to our switch, and through our switch to our provider edge. So hold on one second, because I keep getting phone calls and they're just distracting me. All right, let's rip and rebuild this thing entirely, starting with the switch. All right, you all hold on, please. I'll get right back into this. Hold on. All right, so what I'm going to do is we're going to just try a rip and rebuild both of switch 3 and R3 because the VPLS, the subscriber's VPLS is learning the MAC address for switch 3 through the SAP, physical port 115 with the service delimiting VLAN tag of 20. Uh, switch 3 recognizes R3 through Cisco Discovery Protocol, and R3 also recognizes switch 3 through Cisco Discovery Protocol. So uh, I think it's something software related. So I'm just going to stop these routers, delete them, and we're going to rebuild them. All right, so let's just drag another CPE out of here, and let's drag another switch. Physical port 115 on our provider edge is going to go to port 115 on our switch, which is going to be a trunk. FA10 on our switch is going to go to G00 on our CPE, which again is also going to be a trunk. And we're going to start these two devices and console back into them. All right, so let's start with the switch. I'm going to turn FA10 into a trunk port. I'm going to also turn FA115 into a trunk port and enable VLAN 20. All right, and while spanning tree is taking its time, listening and learning, we're going to go ahead and configure our CPE. Again, it's going to be physical interface gig 00, sub interface gig 00.20. Our encapsulation is going to be .1Q20, and our IP address 172.16.03. And we're going to put this on the same network as our other devices. And spanning trees forwarding how it should. Let's take a look at our forwarding database. Router N7. All right, so it learns the IP address of the switch. So I'm just going to redo my previous commands by pinging the network address from R1, pinging the broadcast address from R2, and we're going to go to R3 and try to ping these hosts individually. Okay, so that's what we'd like to see. So from R1, which is our site in Los Angeles, when we ping our network address, we see that we receive replies from .2, which is our site in New York, as well as .3, which is our site in Dallas. And so we can, we're kind of sure that they're part of the same Ethernet segment at this point. When we ping the broadcast address from our site in New York, we see that we receive a reply from Los Angeles .1 as well as Dallas .3. And when we ping each other subscriber site, which would be Los Angeles, and New York from Dallas, which is R3, those pings are replied to as well. So if we look at our forwarding database on N7, we can see that now we're learning the MAC address of our CPE, starting Charlie Alpha, through our SAP. Likewise, we're learning the MAC address for our CPE terminated on N6, which would be R2 through SDP 101. And we're learning the MAC address for our CPE R1 terminated on N1 through SDP 101. So I'm just going to clear the forwarding database on all of our edges and reissue those ping commands, and then we will verify one more time, and then we'll be done. So what I'll do this time is I'll ping the network address and the broadcast address from all of our CPEs. All right, so when we ping the network address again from Los Angeles, we get replies from Dallas and from New York. So now we're just going to ping the broadcast address. And when we ping the network address from New York, we get replies from Los Angeles and from Dallas. So we're going to ping the broadcast address. And when we ping the network address from Dallas, we get replies from New York and Los Angeles. So we're just going to ping the broadcast address there as well. And so just like with the network address, when we ping the broadcast address from Los Angeles, we get replies from New York and from Dallas. When we ping the broadcast address from New York, we get replies from Los Angeles and from Dallas. And when we ping the broadcast address from Dallas, we get replies from New York and Los Angeles. So let's go ahead and save this configuration. And we can also take a look at our forwarding database with the command show service ID65 FDB detail. And so we have our CPE. This is N1, so let's go back here. The CPE R1, its MAC address is being learned through SAP 115:20. And the MAC address, let's do it this way. So on R1, show interface. All right, so on R1, we see the MAC address is Charlie Alpha 03. And we could see that we're learning the MAC address Charlie Alpha 03 through our SAP. And on R2, we can see the MAC address is Charlie Alpha 04. And we're learning Charlie Alpha 04 through our pseudowire SDP 102.65, which we would expect. And on R3, our MAC address is Charlie Alpha 05. And we're learning Charlie Alpha 05 through the pseudowire SDP 100:65, which we would expect. We could look at the forwarding database on each provider edge. And again, they're the same. Charlie Alpha 03, which is R1. We're learning that MAC through SDP or through pseudowire SDP 102:65. Let's see, R2, which is the MAC address Charlie Alpha 04. We're learning that through our SAP 115:20. And Charlie Alpha 05, which is R3, we're learning that MAC address through our pseudowire SDP 101:65, which we would expect. And on R7, we'll do the iteration again. We're learning our CPE's MAC address, Charlie Alpha 05, through our SAP for R3, which we would expect. We're learning the MAC address for R2, Charlie Alpha 04, through SDP 101:65, that pseudowire, which we would expect. And we're learning the MAC address for R1, which is Charlie Alpha 03, through the pseudowire SDP 100:65, which we would expect. And we're also grabbing the MAC address of switch 1 for whatever reason. Let's go back to our goals here. Yeah, so it looks like that's it. Examine each CPE's ARP table. Okay. Let's see. And by the way, this is our ePipe VLAN 10. Between R1 and R2, if you remember from our previous video. But anyway, so the ARP table on R1 does contain our local interface .1 with a valid MAC address, as well as our interface in New York .2 with a valid MAC address, and our interface in Dallas .3 with a valid MAC address. Let's hop into R2. On R2, we have a valid MAC address for Los Angeles, which is .1, a valid MAC address for our local interface .2, and a valid MAC address for Dallas, which is .3. And in Dallas, we have a valid MAC address for Los Angeles, which is .1, and a valid MAC address for New York, which is .2. And like we've done before, all of these hosts are on the same Ethernet segment. So they all reply to pings to the broadcast address or to the network address. And let's see, we could let's see, let's take a look at some pings. I mean, we might as well. Mpls. All right, so we're going to ping from R1, which is Los Angeles, to New York. And we're going to repeat it, I don't know, 20 times. And here are our pings. And inside the data field is our ICMP echo request. But the important thing here is to recognize that we do have our service label or our inner label of 65 and our transport label or outer label of 71. So we are label switching correctly. We are multiplexing and demultiplexing correctly. And at this point, I would consider our VPLS to be fully functioning. So each of these customer sites are connected to different provider edges in a geographically dispersed fashion, one in Los Angeles, one in New York, one in Dallas. Yet through the use of VPLS, from the subscriber's perspective, all of their sites are plugged into a single switch or are part of a one Ethernet segment or within a single broadcast domain. So again, the service provider, their IP MPLS backbone is emulating that virtual switch for the subscriber sites. And that is the end of the presentation. As always, I appreciate you viewing. And as always, I'm completely open to criticism and scrutiny. However I can improve, please share that with me. If I provided misinformation, if I misspoke, please share that with me as well. In the next video, which will round out our service videos, well, there's going to be another 2 videos. There's going to be one on VPRN and another on IES. And after that, we'll be wrapped up with service deployment on the service router operating system, or the SR platform. Once the service deployment videos are wrapped up, I'll probably do a few more videos, one mainly on BGP, one on, let's see, probably OSPF, though ISIS and OSPF are link state protocols. They're very, very similar. There are some slight differences that I'll highlight in those videos. And maybe even one on QoS, who knows. But again, thank you for viewing, and I look forward to you checking me out next time. All right, bye.